Okay, so just briefly then, we'll just recap what sequences generally are. A basic linear sequence. This one goes up in twos. The first difference is the same every time. The first difference is the difference between each term. So the difference is always 2. So this is a linear sequence. Now, geometric sequence is a nonlinear. Is a type of nonlinear sequence. If you look at the first difference, it goes. The first difference is 1. The second difference, but then the first difference is 2. So this is where the first difference gets confusing. We might think that's the first difference, that's the second difference. That's not the case. The first difference is always the difference between the terms. And then 4. So you can see the first difference keeps doubling. If I do the second difference is 1, and then 2, and then 4. It also keeps doubling. The third difference, 1, then 2. And if I keep doing that, you'll see it just always doubles. So you can keep on doing the first, second, third, fourth difference, and so on. And with a geometric sequence, you'll never get to a constant value. It's different to geometric sequences, and it's different to quadratic sequences, which we'll look at later on. So what is a geometric sequence? Well, what it is, as it says here, is that you multiply it by the same amount each time. In this case, it started off with 1. The first term we can refer to as a this time. So a can be called the first term, or x1, and we multiply it by something called the common ratio, which we call r. It says so down here too. And then we put that to the power. The r is to the power of n minus 1. So, for example, in this sequence we've got here, the first term. So I'll just write this down. So in this example here, we've got the common ratio. Right, I'll do first. The common ratio is 2, and the first difference is the first value xn. The first term is 1. So if I go 1, 2, 3, 4, 5, there's the fifth term. So x5, the fifth term, would be equal to 1. So a r to the power of n minus 1. 1 times 2 to the power of 5 minus 1, which is equal to 2 to the power of 4, which is equal to 2 times 2 times 2 times 2. So if we do that on the calculator, I could do 2 times 2 times 2 times 2, or if I've got a scientific calculator, so I'm just going to do 2 to the power of 4, and that gives me 16, and that's what it is here. So that's how geometric sequences work. Let's just look at why is it that a is x to the power of 1 according to this formula here. If we had n is equal to 1, then the nth term would be x1, and that would be that's the final answer. I haven't showed the working out, so I'm just going to erase this bit here, and we'll do it again. Yes, and I need to also remind everybody that whenever you do a power to 0, anything to the power of 0 is equal to 1. 10 to the power of 0 is equal to 1. 5 to the power is equal to 1. Anything to the power of 0 is always equal to 1. So some of you might work out where this is going to go. So if n is equal to 1, then the first term, the nth term when n equals 1, would be equal to a multiplied by r to the power of 1 minus 1, n minus 1, which n is 1, so 1 minus 1, which is equal to a to the power of a times r to the power of 0, which is just because anything to the power of 0 is 1, it would be a times 1, which is a. So you can see here that the first term, is equal to a. Okay, so that's the proof of why that is the case. Then that's the hard bit. the easy bit is pretty much what is the majority of what you do with geometric sequences, which is just finding out the formula, or predicting the, like if you, maybe I could give you a question now. What would be in this geometric sequence, what would be the 100th term? So I'll pause the video and see if you can tell me what is the 100th term in this sequence. Okay, so I've got my calculator here, so I can show you how I would do this. The 100th term, let's work it out first, work out what the formula is going to be. So the 100th term is going to be, so x100 is going to be equal to a, which is 1 in this case, so 1 times r, which is 2, to the power of n minus 1, which is, n minus 1. Now that is going to be 100 take away 1. So that's just going to be 2 to the power of 99. It's going to be a very big number because we're going to be timesing 2 by itself 99 times. I don't even know what my calculator is going to say, but I think you might need to be familiar with what was I going to say, with standard form. So when we just a quick reminder about standard form, when we want to write very large numbers, let's imagine we had 200 million. Eventually it gets a bit difficult to count all the zeros to work out how big the number is. So I can just demonstrate how big the number is by writing 2 times 10 to the power of 8. And that, so 10 to the power of 8 means 10 times 10 times 10 times 10, and it just makes it a bit easier. You can imagine if it was 2 times 10 to the power of 56, well, I wouldn't be writing 2 and then 56 zeros, because that's just not very useful. So we're going to get a number that's going to be quite large, and it's probably going to be in standard form. So let's just do 2 to the power of 99. So I'll just demonstrate it here how I would do that. So you've got the 2, of course, and then the button on my calculator is that one there. So I'll do that. Up on my screen, I get a little box, and I type in 99, and then equals. And there we go. So a very large number. It's got all these decimal places, but really, if you were to write all those numbers out and then put the rest of the digits after that, so that essentially, rounding up, would be 6. Let's say 6, 3, and then 28 more zeros. Or if you want, just 6 and then 29 zeros. So a very, very large number, and that would be our nth term. So let's just write that down here. So I'm going to put 6.3 times 10 to the power of 29. That'll be our 100th term in this sequence. All right. Let's just stop that video there.